Swayam Prabha. Digital India. Educated India.
Welcome to lecture 21 on the topic vapor compression cycle. We would be continuing the same topic which we have discussed in the previous lecture. Of course, in the previous lecture we have seen the reversed Carnot cycle, which forms the basis for the vapor compression refrigeration cycle. We have seen the temperature entropy diagram and the pressure enthalpy diagram for our ideal vapor compression cycle. There are four major components. One is the condenser, evaporator, compressor and expansion device. When we compare the components of the reversed Carnot cycle with the ideal vapor compression cycle, three components are same, like condenser, evaporator and compressor. Instead of turbine, which is there in the reversed Carnot cycle, we have the expansion device, which could be a capillary tube or a valve in reality. So the process which takes place during the expansion process, that is in the expansion device, is isenthalpic process. Enthalpy at 3 is equal to enthalpy at 4. Process 1 to 2 is isentropic compression. Then we have constant pressure or constant temperature isothermal heat rejection process. Temperature at 2 will be temperature at 2 dash will be equal to temperature at 3, which is equal to the temperature of the condenser. And 3 to 4 is isenthalpic process. There is no change in the enthalpy. Then the pressure, of course, changes from condenser pressure to evaporator pressure. Then the liquid refrigerant is evaporated in the evaporator, that is constant temperature, that is our constant pressure heat addition process. In case of a refrigerator, the desired effect is the amount of heat removed from the space where we want cooling. So it is the COP of the system is refrigerating effect QE divided by power required to drive the compressor. We have solved two numerical. One numerical, in one numerical, the values of the enthalpies are given in the pressure enthalpy diagram itself, and in the second numerical we have to use the refrigerant table. The refrigerant used was R134A. So if we know the enthalpy values H1, H2, H3, H3 is equal to H4, then we can find out the cooling load or the evaporator heat load, refrigerating effect. All these terminologies are same. Power required to drive the compressor and the heat rejected by the condenser. If you look at the energy balance in this cycle, in the cycle which is executed, the summation of evaporator heat load and the work done on the compressor, the work of compression, QE plus WCEO will be equal to QC, Now in this lecture we would be seeing the methods which are employed to improve the COP of the system. Let us go to the contents. Before seeing the methods of improving the COP of the refrigeration cycle, we will compare the refrigeration cycle with the actual cycle, how the actual cycle deviates from the ideal one. Then the methods such as subcooling, superheating, the combination of subcooling and superheating, how does it impact the COP of the system. These things, the theoretical portion I will explain briefly, and I have taken a numerical where the comparison has been made with the base one, like without subcooling, without superheating, the problem which we solved in the previous lecture using the R134A tables, that is without any subcooling or further superheating of this refrigerant coming out of the evaporator. The condition of the refrigerant at the outlet of the evaporator or inlet of the compressor is saturated. If you remember the TS diagram, state point 1 and 2 dash are lying in the saturated vapor state, whereas 3 is lying in the saturated liquid state. So let us see the comparison between the actual and the ideal. The actual cycle is shown in the dotted line, the ideal one is the solid line. Okay. So ideal one we know 1 to 2, then we have got 2 to 3 is constant pressure or constant temperature. This is a pH diagram, so it is a constant pressure line, and the same process will be a constant temperature line on a TS diagram. So 2 to 3 is that condensation process, then 3 to 4 is isenthalpic process in the expansion device, and 4 to 1 is constant pressure heat addition, that is evaporation. So this is QE, let me plot this one, this is QE, this is QE or QC, and this is QC. Okay. So this is the work of compression, this is the work of compression, okay, and this is the heat rejected by the process. So if you see the actual cycle, it deviates from the ideal cycle. Like in actual case, mostly by the time the refrigerant vapor, low pressure refrigerant vapor which comes from the evaporator to the inlet of the compressor, it is slightly superheated. So because this is the saturated vapor curve, this is the saturated liquid region towards the right side of saturated vapor curve is the superheated condition. So this is the condition of the refrigerant before or at the inlet of the compressor, before it is compressed. So point 1 is not in saturated state, it is only in ideal case. In actual case, mostly it will be slightly superheated. So before it is compressed, it is superheated, and 2 dash obviously it is superheated. Then 3 is not saturated liquid exactly, mostly it will be in 3 dash subcooling. If subcooling is cooling below saturation, So 3 shifts to 3 dash, obviously 3 dash to 4 dash it is isenthalpic process. This is a pressure enthalpy diagram. So enthalpy at 3 equal to enthalpy at 4, enthalpy at 3 dash will be equal to enthalpy at 4 dash, and again this one. So we made a comparison for the ideal Rankine cycle, the actual Rankine cycle. Similarly here a comparison has been made between the ideal vapor compression cycle and the actual cycle. Due to the irreversibilities, heat losses, frictional, these are all the primary causes for the actual cycle to deviate from the ideal cycle. Let me explain the subcooling process. Subcooling, here what is done is there is no change in the process 1 to 2. I have taken the condition of refrigerant at the inlet of the compressor or at the outlet of the evaporator as dry saturated. So here it is as usual, state point 1 to 2 is isentropic compression. Then 2 dash is also lying in the saturated vapor region, there is no change in that one. 2 is in superheated condition. Instead of 3, there is a degree of subcooling provided, maybe 5 degrees centigrade. Suppose if the condenser temperature is 30, the delta T, that is the degree of subcooling, is 5 degree, that means the temperature at 3 dash will be 25 degree, 30 my condenser temperature minus the degree of subcooling, 30 minus 5, that will be 25. So expand the expansion process, instead of at 3 it starts at 3 dash, which is in a subcooled region, and this is a TS diagram. So the line will not be perpendicular to the x axis, only the isentropic process line will be perpendicular to the x axis. So 3 dash will be an inclined line parallel to like how we are plotting 3 to 4, we have to plot 3 dash to 4 dash, 3 dash to 4 dash. So this is, we will see what is the effect on the COP of this one. Before, if you look at the COP formula for the ideal case, this is QE divided by work of compression, this is COP. If I want to improve the COP, if you look at the formula, COP will increase if the refrigerant the desired output increases, if QE increases. If the numerator increases, COP will increase. COP will increase if power required to drive the compressor comes down, if the denominator decreases, So we will see how does this subcooling, how does it impact the refrigerating effect. So the subcooling is cooling the refrigerant. This process takes place in the condenser only, before the expansion, before the refrigerant pressure is reduced by the expansion device. So this process takes place in the condenser only. So this is subcooling, this is on a pH diagram. So here H3 is equal to H4, let me write it here, So let us expand this one, and this also expand this one. H3 is equal to H4 without subcooling. With subcooling, H3 dash is equal to H4 dash, isenthalpic process. Okay. So, this is 0.2 dash, this is 0.2 dash, and the other process I have explained. Superheating. So, this is what happened. See, without superheating, point number 1 is on the saturated vapor line. If I consider superheating, so by the time the refrigerant, low pressure refrigerant vapor reaches the compressor from the evaporator in that line, so there are chances that due to the heat transfer, the refrigerant temperature might increase slightly. So, it is like a superheated. So, you can see the temperature also, T1 is more than T1 dash, T1 is not equal to T1 dash. Of course, T1 dash and T4 are same, which is equal to evaporator temperature, but T1 is higher than T1 dash. It is like temperature at 2 is more than temperature at 2 dash. So, this is the degree of superheat, this is the degree of superheat. So, instead of the compression process which starts at the saturated condition, compression starts from here only. 1 to 2 is isentropic compression. It is not 1 dash to 2, it is 1 to, but the condition of refrigerant at state point 1 is superheated condition. So, as the name indicates, so this is the superheating of the refrigerant before it is compressed. And so, this is the process on a pH diagram. Instead of, now 1 has moved from 1 dash to 1. So, initially state point 1 is on the saturated vapor line. Now, in saturated vapor line, because we have to use some state point, so I am using 1 dash, and the one state point 1 has moved to the right side, which is the superheated region. We will see the same problem, base problem, which I have solved for the previous lecture. I will be adding some more data like a degree of subcool or a degree of superheat, whatever it is, and we will see how the COP varies. Subcooling and superheating. Subcooling and superheating. So, here it is subcooling, it is shown very clearly on the TS diagram, and this is superheat. Here you can see this is subcooling. Okay, so this is subcooling. Let me write this one. This is subcooling. This is superheating. This is superheating. So, both subcooling and superheating. So, let me write in the previous, so this is superheating. Okay, or I will write it on a TS diagram, that will be easier, that will be better. Okay. So, this is superheating. Of course, this on a pH diagram, this is also superheating. Okay. And similarly, this is subcooling. Subcooling. So, in the first process only subcooling is employed, in the second one superheating, and in the third one subcooling and superheating. So, this is superheating and this is subcooling in the same process. How does it affect the COP? Okay, so let me erase this one. Okay, so, this is also correct. I have drawn only uniformly in all the TS diagram. This is not wrong, this is also correct. This is superheating, this is subcooling. So, since I have written on the TS diagram, so I have not indicated on the pH diagram. Okay. So, let us with this background, let us solve the numerical. There may be some time constraint because there are 3 methods are employed. Some of the enthalpy will remain the same, some of the enthalpy, suppose if it is subcooling, H3 value will be changed to H3 dash. When H3 is changed, obviously H3 dash will be equal to H4 dash. When we have superheating, so state point 1 dash is moving to state point 1. So, the enthalpy value, entropy value will change corresponding to state point 1. So, maybe if there is some time constraint, I will quickly, in case if any portion is left in this one, I will be covering in the subsequent lecture, because the next 3 lectures are properties of refrigerant, then vapor absorption system and air conditioning system. So, in those 3 lectures, in any one of the lectures, in case when there is a little bit time is there. So, if any portion is not, I am not able to explain in this one due to shortage of time, that will be covered. So, a refrigerator uses R134A as the working fluid and operates. I have taken the same temperature. If you remember, the numerical question which we solved, second numerical question which we solved in the previous lecture, that is lecture number 20, where the evaporator temperature is -18, condenser temperature is 32. So, I have taken the same temperature. The refrigerant at the exit of the condenser is subcooled. So, the subcooled, it is subcooled from 32 to 26. That means the degree of subcool is 32 minus 26, 6 degrees centigrade. Determine the rate of heat removal from the refrigerant space and power input to the compressor, rate of heat rejection COP. Okay. So, now if you see this diagram, if you see the subcooling, okay, this is subcooling. So, this temperature is, okay, this temperature, this is, let me draw the diagram again, otherwise this is the TS diagram. Because the temperature is given, I will plot the TS diagram. This is this one. So, 1 to 2 no change, isentropic compression, and this I will take it as 2 dash. Then we have the condensation, okay, and instead of taking this one, I am taking this portion. So, this is 3 dash, this is 3. Okay. So, this is 4 dash, this is QE, this is work of compression WCO, this is heat rejected by the condenser. Okay. So, this is here, if you see, evaporator temperature is equal to T1 is equal to T, okay, okay. So, this all these temperatures are same, T1 equal to T4 dash, and this will be, let me take this one, this is subcooling, okay. So, this is the subcooling diagram. So, I will take 3, without subcooling is 3 to 4, with subcooling is 3 dash to 4 dash, okay. So, from 3 to 3 dash, and this will be actual sub, okay. Three to 4, okay. 3 to 4 is without subcooling, 3 dash to 4 dash is subcooling. So, 3 dash to 4 dash is subcooling, 3 dash to 4 dash is subcooling. If you see the temperature here, so this is T1 equal to T4 equal to, this is equal to T4 dash, this is equal to -18, this is -18, and if you see this temperature, condenser temperature will be equal to T2 dash will be equal to T3, that is equal to 32 degree centigrade. Temperature at 3 dash is 26. So, this temperature is given as 26 degree centigrade. So, degree of subcool, delta T of subcooling is equal to T3 minus T3 dash. T3 is condenser temperature, which is 32, T3 dash is 26. So, degree of subcool is 6 degree centigrade, 6 degree centigrade. Okay. Now, how to find out the enthalpy at 1? 1 is lying on the saturated vapor line. So, it is saturated vapor enthalpy. So, corresponding to, so enthalpy at 1 is equal to Hg at -18 degree centigrade. From the refrigerant used is R134A. So, for R134A table, okay, there is no change. So, like for the previous problem, whatever the enthalpy which we have got at state point 1, the same value. So, that is what I have found here, okay, because there are 3 methods are there, I will quickly explain. So, H1 equal to same value 387.9 kilojoule. Similarly, we can find out the entropy, at 1. So, that also I will write it H1. Similarly, S1 is equal to Sg at -18 degree centigrade, okay. So, both these things from the table, okay. Let me, due to time constraint, let me not write. So, this is from R134A table. So, H1 and S1. Again here temperature T2 is unknown, T2 is unknown. like previous method, consider the process 1 to 2. Okay, find out this one, S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash, same formula. Okay, S2 minus S, let me, okay, the same formula. See here, process 1 to 2 is isentropic, S2 minus S2 dash is equal to Cp of vapor into ln of S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. What is S2? S2 is nothing but S1, but S2 is equal to S1 since 1 to 2 is isentropic process, compression process. Therefore, S1 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. Again, let me emphasize here, entropy at S2 dash entropy is equal to vapor entropy, because this is also lying on the saturated vapor curve. The only difference is S1 is at minus 18 degrees centigrade. Okay, sorry. S1 is at minus 18 degrees centigrade evaporator temperature, S2 dash is at condenser temperature 32 degrees centigrade. So, the only difference is this one. This is minus 18, this is 32 degrees centigrade from the steam table. From R134A table. From R134A table. Once you found out S2 dash, substitute here, all these values are known, and Cp of vapor, because we do not know T2, Cp of vapor should be evaluated at only T2 dash, at T2 dash, that is also at 32 degree centigrade, 32 degree centigrade. So, substitute, you will get the value of T2. So, that is what I have shown here. Okay. See, for example, suppose if you take the entropy and enthalpy at state point 1, let me just do it once again. H1 equal to Hg and S1 equal to Sg. This is the refrigerant table, R134A. This is temperature. Okay. So, this is temperature, R134A. So, corresponding to minus 18, okay, read out Sg and Hg. Okay. So, same values you will get, same values of, this is S1, this is H1. Okay. And next one is corresponding to 32, we are finding the entropy at state point 2 dash. So, this is, read out this value 1.7142, there is no change compared to the value which we have taken for the previous problem. And because we do not know T2, we cannot take average of T2 and T2 dash at this stage. So, we are taking the Cp of vapor, this is Cp of vapor, okay, this value. So, all these values I have taken, okay. See here 1.058, 1 so same values. So, to find out, you will get the same T2, because we have not changed the condenser temperature and evaporator temperature. So, T2, then with the T2 I can find H2. How to find out the H2, this one? Superheated enthalpy is equal to saturated enthalpy plus Cp of vapor into higher temperature minus lower temperature. Here H2 dash should be H2 dash is equal to Hg at T2 dash is equal to 32 degree centigrade, and this Cp, because now I know T2 and T2 dash. So, using this formula I can find T2, which is the same temperature 39.5 degree centigrade, 39.5 degree centigrade. So, H2 dash I can find, H2 dash how you found, like S2 dash, saturated vapor enthalpy corresponding to 32 degree centigrade, and similarly Cp of vapor is equal to, should be taken at average temperature of, let me write it clearly, Cp of vapor is equal to, let me write it again, I think there is some technical issue. Cp of vapor is at the rate average temperature of T2 plus T2 dash by 2. T2 is 39.5 plus T2 dash is 32 by 2. This is approximately 36 degree centigrade. So, corresponding to this 36, we have to take the value corresponding to 36. I am taking the Cp of gas 1.088. So, that is what I have substituted here 1.088. See 1.088, this is the value I have taken. I have given a detailed procedure. From this, using the value of H, you can find out H2. You can find out the value of H2. Substitute here, therefore, you can find out H2. Okay. So, H2 comes around 424.1 kilojoule per kg. 424 using this formula 424.1 kilojoule per kg. Now, we have found H1 and H2. We have to find, but if you look at the diagram, here we are considering subcooling. I want temperature at, I want the enthalpy at 3 dash. Without knowing the enthalpy at 3, we cannot find the enthalpy at 3 dash. So, there is a formula to find out the enthalpy at 3 dash, because we know the temperature at T3 dash, that is it is subcooled from 32 degree centigrade, that is condenser temperature, to a temperature of 26 degree centigrade. So, now to find H3 dash, this is not the case in the previous problem. H3 dash we have to find only if subcooling is there, otherwise H3 equal to H4. How to find H3? State 3, let me take state 3. H3 is very easy. H3 is in the saturated liquid line. This is the saturated liquid line. So, H3 is equal to, here the temperature is 32. So, H3 is equal to liquid enthalpy at 32 degree centigrade, liquid enthalpy at 32 degree centigrade. So, if you look at the table, 32 liquid enthalpy is this one, 244.55, H3 equal to 244.55. So, H3 is equal to 244.5 kilojoule per kg, which is equal to H4. But because we are considering subcooling, we want only H3 dash and H4 dash. But without knowing H3, we cannot find H3 dash. So, there is a formula for H3 dash. If you look at the diagram, 3 dash is lying on the subcooled. This is, if we want to find superheated, this is superheated enthalpy, superheated enthalpy, superheated enthalpy, okay, superheated enthalpy. But in case of 3 dash, it is in subcooled region, therefore, subcooled enthalpy, subcooled enthalpy H3 dash is equal to, if I want this point, I know this enthalpy, this saturated enthalpy, saturated liquid enthalpy, if it is superheated, you have to put plus, if it is subcooled, because it is below saturation, superheated condition is above saturation. So, saturated enthalpy plus Cp of vapor into delta T. If it is subcooled, means saturated enthalpy minus Cp of liquid. If it is superheated, means it is vapor. If it is subcooled, means it will be liquid. So, Cp of liquid into delta T. What is the delta T? 3 to 3 dash, that is the subcooling process. Higher temperature minus lower temperature, T3 minus T3 dash. I know T3 32, I know T3 dash, it is given in the problem 26. H3 I have found from this one corresponding to 32. Cp of liquid I have to find. Again, how to find Cp of liquid? Cp of liquid should be evaluated at these average temperatures. Cp of liquid to be found out for the average temperature of T3 plus T3 dash by 2. T3 plus T3 dash by, what is T3? T3 is 32, T3 dash is 26 divided by 2, that is 58 by 2, that is equal to 29 degree centigrade. That is equal to 29 degree centigrade. Okay. So, that is this T3, this is 29, corresponding to 29, I have taken the Cp value as Cp of liquid as 1.442. If you look at the table, okay, we do not have for 29, but we have got 28 and 30. We have got 28 and 30. So, we have to take the average of these values, okay. Cp of liquid at 28 degree, this is this value, and Cp of liquid at, okay, let me write this value. I will write it in the space itself, otherwise it will be confusing here. So, how to find this value? Cp of liquid at 28 degree centigrade plus Cp of liquid at 30 degree centigrade, because we do not have the value for 29, average by 2. So, this will give the Cp of liquid. So, substitute, you will get H3 dash, H3 dash is equal to, the calculated value is, I have given the detailed calculation, 235.8 kilojoule per kg. This is equal to H4 dash. Now, once you know this one, you can substitute in the formula. Heat removal is, now the heat removal is, okay, now the heat removal is, if you see the enthalpy, if you see the cooling effect, refrigerating effect, it is from H1 to H4 dash, not H4, H1 to H4 dash. See the formula here, rate of heat removal from the refrigerator, it is H4 dash, not H4. There is no change in the work of compression. Rate of heat rejection, instead of H2 minus H3 without subcooling, it will be H2 minus H3 dash. So, the difference is here and the COP of this one. Okay. So, we can calculate the COP, again the energy balance you can do, the desired effect, that is the desired output, that is the refrigerating effect, plus the work power required to drive the compressor will be equal to the heat rejected by the condenser. Okay. So, the next one, the second one, I have taken the same condition, evaporator temperature, condenser temperature, refrigerant is superheated, that means, okay, see here, let us take the superheating diagram. Temperature at 1 dash is minus 18, whereas temperature at 1 is minus 10, So, let me draw this diagram. Here there is no subcooling, but there is only superheating, okay. Because it is a quite lengthier problem, I will try to, because now the procedure is same. So, let us draw the TS diagram. So, here it is slightly heated, then it is 1 to 2, then we have the heat rejection process 2 to 3, 3 to 4, I have drawn a TS diagram 3 to 4, this is temperature, this is let us extend this one, this is the entropy line, okay. So, this is like this one, this is 1 dash. Now, 1 has moved from the saturated vapor region to the superheated region, and of course, this point is 2 dash. Okay. So, this is condensation process, this is evaporation process, and this is work of compression, and this is throttling. Okay. So, here the enthalpy at 3 equal to enthalpy at 4. Now, 1 has shifted from, 1 has state point, let me write here, superheating, state 1 has shifted from saturated vapor line to superheated condition, to superheated condition. Now, let us plot the temperature, because the procedure is more or less same. Here the enthalpy at 3, like the base case, enthalpy at 3 equal to enthalpy at 4, this is saturated liquid enthalpy corresponding to this temperature. This temperature remains the same, 32 degree centigrade. This temperature is minus 18. So, that means T1 dash is equal to T4 is equal to T evaporator is equal to minus 18. But here the temperature is minus 10.
here the temperature is minus 10, which is given because it is this is superheating. Okay, in the previous case there is no superheating, there is only subcooling. So this is minus 10 degrees centigrade, which is given. So these are all the data given, and so this is minus 10 degrees centigrade, and if you see, write the temperature on the condenser side, T2 equal to T2 dash is equal to T3 is equal to condenser temperature is equal to 32, that is positive temperature 32. Okay. Okay. So there is no change in the enthalpy H3 equal to H4 when we compare with the base problem, not with the previous problem. Previous problem was subcooling is involved. So subcooled enthalpy is equal to saturated enthalpy minus Cp of liquid, because it is subcooling it is liquid, if it is superheating it is vapor. So if it is superheating we have to add plus sign to the saturated enthalpy, if it is subcooling we have to subtract from the saturated liquid enthalpy. Okay. So now here the enthalpy value at 1 will change, because for the previous one it does not change, because 1 is lying in the saturated vapor region. Okay. So I have given the procedure. State 1, see state 1 is superheated, again it is in superheated condition. So H1 is equal to this enthalpy is in 1. Okay. So 1 is in superheated state 1. State 1 in this case is superheated enthalpy. Superheated enthalpy H1 is equal to the corresponding saturated enthalpy is H1 dash plus Cp of vapor into this temperature difference T1 minus T1 dash. Now how to find H1 dash? H1 dash is corresponding to minus 18 degrees centigrade, the saturated. So that is very easy. H1 dash is equal to vapor enthalpy at minus 18 degrees centigrade, which is the T1 dash temperature. Okay. So let me write this one, at this temperature at T1 dash is equal to minus 18 degrees centigrade. Now what is the Cp of vapor? Because I know T1 and T1 dash, I can find out the average temperature, and for that average temperature I will take the specific heat value. So Cp value is Cp of vapor should be taken for the average of T1 plus T1 dash by 2, T1 plus T1 dash by 2. Okay. So if you see the procedure, T1 plus T1 dash by 2 minus 10 minus 14 degrees centigrade. So I have taken the value corresponding to minus 14, Cp value is 0.827. Okay. So we have got minus 14, this is minus 14. Okay. So this is temperature, this is R1348 table, same refrigerant, and Cp of vapor, see this is Cp of vapor. Okay. So this is 0.827, this is what I have taken, Okay. So next, so this is the only difference, this is one difference of course. Then we can find H1, H1 dash no change, H1 dash no change. How I have taken H1 dash? H1 dash is 3 same value corresponding to minus 18, okay, corresponding to minus 18. This is okay, this entropy 387.9, no change. So substitute in this formula, you can find H1 dash, you can you can find H1 dash. So using this formula, because we know all these values, this one we know, you can find out H1 dash. Okay. Then from 1 to 2 is isentropy compression, we can find out follow the procedure. Here state 2, I have written the same formula, S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. Now this temperature at 2 will vary, it will not be 39.5, follow a similar procedure. Temperature at 2 is 47.3. This is because in the previous case T1 was minus 18, T2 was 39.5, but here T1 is different, T1 is minus 10. The actual compression starts from here only, from here to here only. So the compressor is compressing from a temperature of minus 10 which is a higher temperature than the previous case. So, this T2 also will change. T2 is not same like 39.5, but the procedure is same. Okay. 1 to 2 is isentropic process. 1 to 2 is isentropic process. So, let me explain with this one. So, similarly you can find entropy. How to find entropy? Entropy at 1 is equal to use this formula. Entropy at 1 is equal to saturated entropy at 1 dash plus Cp of vapor into T1 dash by T1. So, using this formula, okay. I know all these values. Whenever we have temperature ratio, substitute in Kelvin, and Cp of vapor to be taken for the average temperature. Okay. So, already we have taken 0.827. Okay. Find out entropy. Entropy at 1 is equal to entropy at 2, and so S1 minus S2 dash is equal to Cp of vapor into ln of T2. So, the new value of temperature 2 is 47.3. Okay. In temperature 2 is 47.3 and not 39.5, because the inlet temperature has changed. Inlet temperature is not minus 18, it is minus 10. Minus 10 T1. From T1 to 2 only the compression starts. It does not start from 1 dash. Okay. So, now the procedure is same. State 3 liquid enthalpy 244 corresponding to 32. Okay. How to find the corresponding to 32? This is R134A. Okay. This is table. Liquid enthalpy. This is liquid enthalpy 244.5, no change. This is similar to the base case, not the previous problem. If it is subcooling, we have to find out the subcooled enthalpy. Okay. So, if you substitute the values, we will get, and similarly how to find H2, how to find H2 here, this enthalpy plus Cp of vapor. Okay. So, superheated enthalpy H2 like the previous one, enthalpy H2 is equal to the corresponding saturated enthalpy plus Cp of vapor into T2 minus T2 dash. And here how to find H2 dash? H2 dash is equal to Hg. Okay. H2 dash is lying on the saturated vapor line. So, H2 dash is equal to Hg at 32 degree centigrade, because the temperature at T2 dash. How to find the Cp of vapor? Cp of vapor is at the average temperature of T2 and T2 dash divided by 2. So, T2 is, we have found the new value of T2 is 47.3 plus T2 dash is 32 divided by 2. So, that is 79.3 degrees centigrade divided by 2, that is approximately 40 degrees centigrade. So, Cp of vapor at 40. So, if you see this one, see I have taken the Cp of vapor at 40, it is 1.120. Let us look at the table. Cp of vapor at 40, what is this value? 1.120, this is what I have taken and substituted. And enthalpy at 3 you can find out easily. What is the enthalpy at 3? Enthalpy at 3 equal to liquid enthalpy corresponding to 32, like we have done before. State 3, so this is state 2. Enthalpy at 3 is equal to liquid enthalpy at T3. At T3 the temperature is 32 degrees centigrade. This is T2 dash. Okay. T2 dash and T3, say all are lying in the same line. Temperature at 2 dash is equal to temperature at 3, which is condenser temperature. That is what I have written very clearly. Okay. So, I have written very clearly, these temperatures are same, these temperatures are same. Once we know this one, then substitute in the formula. So, once we know H3, that is equal to H4. So, H3 corresponding to 32, what is the value? Corresponding to 32, the value is 244.5. So, let me write this value. So, this is equal to 244.5 kilojoule per kg H3, this is equal to H4. Now, I know enthalpy 1, 2, 3, 4. Okay. Substitute in the formula. The formulas are not going to change. QE equal to H1 minus H4. This is without subcooling. If it is subcooling, it is H4 minus H4 dash. Then the power input to the compressor, this is from H2 to H1, but of course the state of point 1 has moved from saturated vapor to superheated region. So, there will be change in the work of compression. Heat rejection, no change in the formula, H2 minus H3, we are getting the perfect energy balance. So, this is case number 2, and case number 3 is both subcooled, I have taken both subcooling and superheating, superheated. Okay, follow a similar procedure, Okay. So, here if you see state point 1, okay, this let me explain this diagram, because time may not be there to explain the numerical question completely, but the concept we have explained the procedure for solving problem with subcooling with superheating. Now, this is the combination of both subcooling and superheating. So, if you take the diagram subcooling and superheating here, okay. So, this is the subcooling, this is the superheating. The refrigerant is subcooled before it is throttled, and here it is superheated before it is compressed. Okay, let me draw this diagram and again explain so that you will understand, it gives better clarity. Okay, so I will, this is the TS diagram for subcooling and superheating, So, here there is some superheating takes place. 1 to 2 is isentropic compression. Okay, then this is isothermal heat rejection. This is a TS diagram. And here I have taken this one. So, this is subcooling. Subcooling is shown by the dotted line. Okay, so this is, let us draw like this, and this is isothermal heat addition process. This is QE, this is work of compression, this is 1 dash, this is 2 dash, okay. This is 3, this is 3 dash, this is 4 dash, and of course this is 4. The dashed line represents subcooling process, and so here 1 dash to 1 superheating, and 3 to 3 dash is subcooling. So, this is superheating, this is subcooling. Okay. So, let us write the given data and plot the temperature so that you will understand. Once we are clear with the temperatures, we know how to find the superheated enthalpy, saturated enthalpy plus Cp of vapor. If both temperatures are known, we have to find out the average temperature and take the property specific heat. Similarly, subcooled liquid is saturated liquid minus Cp of liquid, not vapor. Instead of plus, you have to put minus and delta T, degree of subcooling. Okay. So, let us write the given data. Here it is 32, 20, there are 4 temperatures are given. Okay. Let us take this one. So, this is the evaporator temperature. So, this is minus 18, this is minus 10, okay, and this temperature is, let me plot it clearly because it is not clear. Okay, let me write this point bottom so that the lines are visible. This temperature is Tc is equal to 32. And what is the degree of subcooling temperatures that is given in the problem? Let us take. It is the same subcooling which was given for the problem which we solved today in this lecture number 21. So, subcooling starts from 32 degrees centigrade to 26 degrees centigrade, that is delta T of subcooling is 6 degree. So, this is 26. So, this is 26. Okay. So, if you see the evaporator temperature is minus 18, by the time refrigerant vapor from the evaporator to the compressor reaches its temperature, there is a slight superheating. So, it changes from minus 18 to minus 10. So, at this point the temperature is minus 10, then the condenser temperature is 32, there is a degree of subcooling 6 degree. So, the temperature here is this one. So, if you see, it is proportionally it is increasing as we move along the y axis, Of course, T2 is the maximum temperature that is attained in the cycle, okay, T2 that. And how to find this enthalpy? H1 dash is saturated vapor enthalpy, H1 dash, let me write H1 dash is equal to vapor enthalpy at what, at temperature T1, T1 dash. What is the temperature at T1 dash? So, let me write T1 dash is equal to T4 is equal to T4 dash is equal to T is equal to minus 18. Okay. First let us write the given temperature. Then T1 is given as minus 10. Then T3 dash is given as 26 degrees centigrade. Then the highest temperature, not the highest, next to the highest temperature is at T2, which we have to find out, and T3 equal to T2 dash is equal to condenser temperature. This is evaporator, this is condenser. Condenser temperature is equal to 32 degrees centigrade. So, I have written the temperatures. Now, H1 dash and S1 dash, let me write it so that you will be very clear. H1 dash is equal to Hg at T1 dash is equal to, what is the T1 dash? Minus 18 degrees centigrade. Similarly, S1 dash is equal to Sg at this temperature, minus 18. Now, similarly, how to find the enthalpy at 2? This is state 1 dash, state 1 dash. How to find the enthalpy at 1? Enthalpy at 1 is equal to enthalpy at 1 dash plus Cp of vapor into delta T, T1 minus T1 dash, and this Cp of vapor to be taken at the average temperature of T1 plus T1 dash by 2, the same procedure. Now, how to find enthalpy at 2? Let us go to state point 2, state point 2, enthalpy at 2 is equal to H2 dash plus Cp of vapor into T2 minus T2 dash. Again the Cp of vapor to be found out average temperature of T2 plus T2 dash by 2. So, it is a combination of the subcooling and superheating. Obviously, it is a quite lengthier problem. How to find H2 dash? In this H2 dash is Hg at 32 degrees centigrade. So, it is very simple. Once if you are clear with the basics, without looking at the diagram, we can write. So, this is because 2 dash is lying on the saturated enthalpy. Now, come to this point 3, okay, come to this point 3. So, let me write state 3 here. State 3, it is very easy. State 3, saturated liquid line corresponding to 32, temperature at 3 is equal to temperature at 2 dash. Okay. So, enthalpy at 3 is equal to liquid enthalpy, this is liquid enthalpy at T3 is equal to 32 degrees centigrade. Now, how to find H3 dash? H3 dash is subcooled enthalpy. So, subcooled enthalpy is equal to saturated enthalpy minus Cp of liquid into delta T, T3 minus T3 dash. And again, how to find this enthalpy? This is, okay, let me write it here. H3 we have found, H3 we have found from this one. Liquid Cp is average of these two temperatures. T3 is 32, T3 dash is 26. So, 32 plus 26, 58 by 2, we have to find out for 29, average of 28 and 30, okay, which we have done before. So, this is very, very clear, and the detailed, the values also I have substituted for this case. Okay. So, we are getting T2 is 47.3 and here H1, H2, H3 dash, the energy balance. Okay. So, I have made a comparison of all the methods which are employed to improve the COP of the system. This is with for the numerical question which we solved in lecture number 20, the numerical question number 2. Okay. So, I have taken the same temperature, condenser temperature is 32 degrees centigrade, evaporator temperature is minus 18. If it is subcooling, I have taken a degree of subcool of 6 degree, that is 32 minus 6, 26 degree, and the superheating I have taken from after superheating, due to the superheating of the refrigerant vapor before it enters the compressor, the temperature has changed from minus 18 to minus 10. So, the parameters are all same, the evaporator condenser temperatures are same, subcooling from 32 to 26, superheating from minus 18 to minus 10. Now, if you see, again I have used the same green color for wherever there is increase in that particular parameter. blue color represents the decrease in that value, and the sandal color represents there is no change. When we analyze the vapor compression refrigeration cycle for a condenser temperature of 32 and an evaporator temperature of -18 with a subcooling degree of subcooling of 6 degree, that is a subcooling temperature of 32 minus 6, 26 degrees centigrade, the cooling capacity increases, because if you see this one, with subcooling the refrigerating effect is Q1 minus Q4 dash, Q1 minus Q4 dash. So, the delta H increases, delta H increases. It is not H1 to H4, it is H1 minus H4 dash. Okay. So, let me write this one before, because still 5 minutes are there. So, suppose if you take subcooling, in subcooling this is let me write it here. Here the desired effect is H1 minus H4 dash and not H4. So, there is a increase in the delta H. Okay. So, this is and here the work of compression is m dot r into H2 minus H1. It is not 1 dash. Okay. Of course, here also multiply by the mass flow rate of the refrigerant, mass flow rate of the refrigerant. So, if you see this table, okay, so let us compare the results and see why the COP is varying. Okay. So, this is the one. So, there is an increase in delta H. So, Q numerator increases. So, QE is increasing, COP is also increasing. There is no change in the work of compression. So, the COP is increasing. Now, VCR with superheating, in fact, the cooling capacity or the refrigerating effect decrease, it also increases, but it is less than subcooling. The amount of the magnitude to which the cooling capacity increases with subcooling for the same operating condition is slightly more than for the superheating case. Work of compression increases, but because of this there is a reduction in the COP marginally from 3.96 to 3.88. When we have VCR with subcooling and superheating, the cooling capacity is highest, the work of compression of course that is also highest, the COP is also more than subcooling, but it is more than both subcooling and superheating, but it is less than only with subcooling. Okay. So, to summarize, we have seen a comparison between the ideal vapor compression cycle and the actual cycle due to the irreversibilities, losses due to heat transfer and friction. The actual cycle deviates from the ideal cycle. We have seen the 3 methods, subcooling, superheating and a combination of subcooling and superheating, how it does affects the COP of the system by solving a numerical question. So, with this I conclude the lecture number 21. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.